Hello, you fine physics folks. Let's look at some examples of using Newton's second law to try and find things involving acceleration, net force, and various forces involved in problems like this. We may have to include a little bit of kinematics while we're working through these problems as well. You're going to be using your sheet that was titled Net Force and Motion, and we're looking at example number 7. This is as far as we got yesterday. So let's jump in and have a look at that example. Example number 7 here says, determine the force of air resistance acting on a 60 kilogram skydiver at the instant she is accelerating at 4.5 meters per second squared down. First thing we're going to want to do is draw our directions. So I'm going to make my down direction negative, and I'm going to make my up direction positive. As usual, those could be flipped. Just means your final answers would have the opposite sign. And I'm going to say, okay, I notice right now that I don't have the force of gravity here, but I do have the mass of my skydiver here. So I could be able to figure out that force of gravity. So let's start there. We're going to say our force of gravity is going to be m times g. Mass is going to be 60 kilograms, and g is going to be 9.8, but g is down, so I'm going to make this negative 9.8. Okay, that's going to work out to negative 588 newtons, and it's a negative, so we know that that force of gravity is going to be down. I don't want to put directions back in yet because we're still kind of in the middle of the problem here. So we say, okay, we found the force of gravity down. That's good. We want to know the force of air resistance. We can't find that yet, but when we think about what we need to find that, right, here's our force equation. Our force equation says net force is the sum of the forces, and the sum of the forces, if we write them all out, is force of gravity and force of air resistance. Air resistance is the one we want. That's the one we want to get. We know force of gravity. We want force of air resistance. We got to figure out net force. Thankfully, we have another formula for that, right? Our formula for net force is just Newton's second law. Net force is mass times acceleration. Okay, our mass, we were already given that in the problem. It was 60. And our acceleration, we were giving that in the problem as well. It's down, so it's going to be negative 4.5 meters per second squared. Okay, we're going to plug that in. And we say, all right, 60 times negative 4.5, we're going to end up with negative 270. Again, that's newtons. So that is the sum of the forces. It's overall with force of gravity and air resistance, we have more downwards force than upwards force by 270 newtons. Let's plug that into our equation now. Overall, our force is negative 270 newtons, so 270 newtons down. Our force of gravity is negative 588. And then we've got our force of air resistance, which we know is going to end up being positive because it is up. So force of air resistance. Okay, to solve this equation, I'm going to add 588 to both sides to move this one over. That means we're just going to have force of air resistance left on the right-hand side. And on the left-hand side, we've got that 270 plus 588. We're going to end up with 318 newtons. Okay, so I haven't put units in yet or direction, but I notice I have a positive answer. So let's write our final answer. We're going to say the force of air resistance is equal to, now I'm going to have to round this off. Looks like this has got to be 2 sig figs. So I'm going to round this off to 320. Put in our units, that's newtons, and our direction, we know it was positive, and it makes sense that our air resistance would be up because it's a frictional force and it's resisting our motion. So we'll draw a box around that, and there we are. We're all done number 7. We said we wanted to find the air resistance. We had our force equation. We knew we could calculate force of gravity, and we could calculate net force with the stuff we had, and that allowed us to plug in those pieces and get that one piece we don't have, air resistance. Okay, let's move down to number 8. Okay, for number 8, let's consider what we need to get here. We say if we write our force statement, we'll say good old net force is going to be our two forces. We've got our applied force pushing us forward, and we've got our force of friction pushing us back. I guess I should say what the question is. A 300 kilogram motorbike accelerates from rest to 30 meters per second. So it accelerates, we know that, while covering 200 meters. If friction amounts to 3,400 newtons, determine the force applied by the bike. Okay, so here's what we've got so far. I know that force of friction, it's just given to me in the question. I know that I want this applied force here. And so I'm going to need to figure out what this net force is. And if I can figure that out, the rest should fall into place. So let's try and figure out the net force. We have a formula for net force, right? Newton's second law. Net force is mass times acceleration. But I don't have the acceleration. So my first step that I'm going to do here is I got to find that acceleration. I might want to actually write step 1 on here, just to remind myself what I'm doing. I'm going to find the accel. Let's go for it. Okay, so to find the acceleration, I'll say, let's use a little bit of kinematics, right? We know the motorbike accelerates from rest, so we know our initial velocity is 0. We know that it covers 200 meters, so our displacement is going to be 200. We know that its final velocity is going to be 30 meters per second. That's what it speeds up to. And our final part for this, we say, what's our acceleration? We're not sure. We're going to have to calculate that. Okay, let's do some kinematics. Here we go. So we're going to say, what kinematics formula do we want for this? Looks like the one that doesn't include time is going to be this one here. Final velocity squared equals initial velocity squared plus 2 times acceleration times displacement. And I suppose I should have chosen my directions here. A little neglectful of me not to do that. We don't really need them much for this problem, but always good forward to put them on. So let's have a forward and a back. Forward we'll call positive, back we'll call negative. Let's plug our stuff into our equation here. Final velocity is 30 squared. Initial velocity, I can just put an arrow through that because it's 0. And then I've got 2 times my acceleration, which I don't know, times my displacement, which is 200. So we're going to end up with 30 squared is 900. 2 times 200 is 400 times acceleration. So my acceleration is 900 divided by 400. That's 2.25 meters per second squared is my acceleration. Okay, I got my acceleration. That's great. Let's go back up here and let's find net force. We're going to say this is going to be step 2. Find our net force. Well, we know we got a formula for that. Net force is mass times acceleration. Mass is 300. Acceleration we calculated previously, it's 2.25. So we'll say that's 675. This is newtons because it's a force. So our total force is 675, but we know we've got a forward force and a frictional force. When we add those together, we get that 675. Let's go back to this original force statement that we had here. So we're going to call this our step 3. Here we go. We're going to say our net force is the applied force plus the force of friction. Our net force we calculated was 675. Our applied force we don't know, but we want to know it. And our force of friction is given in the question. It's 3,400 newtons. We know that's got to be a negative number. So we'll add that negative number on there. Okay, if we take 3,400 and add it to both sides, we're going to have solved this. I'm going to scroll down just a bit to give me a little more room here. And I'll say, okay, this works out to be 4,075 newtons is my applied force. So if I want to write that as a final statement, I'm going to say my applied force. Let's round this off, right? How many sig figs? Looks like 1. Ooh, okay. We're going to round off to 1 sig fig. So I'm going to say 4,000 newtons. In my direction, in this case, it's an applied force, so that's forward. FWD. Okay, there's my final answer. Let's put a box around it to show that's our final answer. There we are. Let's move on to our last one now. Thanks for hanging in there with me, folks. This is our last one. A 90-kilogram cyclist, initially at rest, exerts a force of 180 newtons west for 10 seconds. If friction amounts to 135 newtons east, determine his displacement during this time. Let's pick our directions first. We got east going this way and we got west going this way. Since west is the first one that's mentioned, and that's where our exerted force goes, and friction is east, let's call west positive and east negative. Again, you could pick the opposite. That would be totally fine. Okay, this one's a little different. This is kind of the opposite of example 8. We don't have enough information to find displacement, so we have to find the acceleration using Newton's second law. However, we're going to need to find the net force first before we can do that. So let's do our step 1. We're going to find our net force by looking at the force equation. So net force is the sum of the forces. That's the applied force. And that's the force of friction. Those are our two that are involved there. Our applied force we're given right in the question. It's to the west, so I'll write 180 newtons as positive. And then I got my force of friction. That's also in the question. I'm going to make it negative because it's going to the east. So negative 135. Add those two together, we end up with a positive of 45 newtons. That means 45 newtons to the west. Let's sneak up here and we're going to do step 2. In this step, we're going to find what's our acceleration. We don't know it, but we do have Newton's second law. We can figure it out. It's mass times acceleration. We got our net force previously. It was 45 newtons. Our mass is 90. Let's plug that in. And we got our acceleration left over. We don't know what it is. We're going to figure that out. Divide both sides by 90. We end up with an acceleration of half, 0.5 meters per second squared. It's a positive number, which means the acceleration is towards the west. Makes sense, because our applied force is bigger than our frictional force. Okay, now we're going to rely on some kinematics. We're going to go back to kinematics for our final step, step 3. Let's see what we know and what we need to know. We see it's initially at rest, so our initial velocity is 0. We know that our time is 10 seconds. We know that our acceleration is 0.5 meters per second squared because we calculated that. And we want to know our displacement. We don't know what it is. Okay, what equation are we going to use for this? I notice the one that's missing is final velocity. So that means the equation we're going to use for this is displacement equals initial velocity times time plus 1/2 times acceleration times time squared. Let's plug some stuff in here. We say initial velocity is 0, so 0 times anything is 0, so that whole term is gone. All we're left with is 1/2 times our acceleration, which is 0.5, times our time, which is 10, but the time is squared. Okay, we say we square 10, that equals 100. Multiply it by 0.5, that would be 50. Multiply it by 1/2, which is the same as 0.5, it would be 25. So you end up with 25. It's a positive number. So that means west. So let's write our final statement here. We'll say our displacement equals Now, what's we going to round off to? Looks like 2 sig figs, because we start with 2, so that's our smallest number, so I'll have 2. 25 meters. We noted it was positive, so we can say that's to the west. There we go. Quick little recap. We're going to have to mix our skills of dynamics, which we've just learned, and kinematics, which we've learned before. It's always good to say, do we have net force? If not, could we calculate it? Do we have acceleration? If not, could we calculate it? Could we use Newton's second law to calculate any of those? Could we use kinematics to calculate any of those? Think to what your final thing is that you need and try and work backwards from there. Okay, that's it. Good luck, folks. Work hard, work smart. Let's see how you do.